let's say we focus on a ring here. Okay, so this is the ring. We are basically, this is a cylindrical pipe. So if you want to think about this ring here, so we have in radial direction, we have heat transfer, and then we have mass flow in x direction. So temperature is at the left phase is T, at the right phase is dt by dx times dx. This is the Taylor expansion, delta x away from the T. And again, this is QR, and this is delta R away from that one. Okay, so if this is delta R, this is QR, and this is QR plus delta R. So now the difference between these two heat transfer rate at R and the R plus dr should be equal to, due to the change in the internal energy, m Cp delta T. And m here is the differential mass flow rate across this control volume. So if I rearrange this equation, the m Cp, and this difference is dt by dx times dx. So we have QR minus QR, and you can Taylor expand this, dqr by dr plus dr. So if you eliminate this, so you get minus dqr by dr times dr. So the differential mass flow rate is density times velocity times 2 pi r dr. Okay, so that means this is the differential mass flow rate. So in other words, m, so if you know the velocity, rho times u times cross-sectional area is going to give you mass flow rate, right? If you take the derivative of that, so this is pi r squared. If you take the derivative, you got 2 pi r dr, rho u, this is the mass flow rate. And heat transfer rate is basically in radial direction, we use the Fourier's law, K times dt by dr multiplied by the surface area, 2 pi r dx. So this is again a cylindrical shell. So 2 pi r dx is going to give us the inner surface area. So the flux multiplied by the surface area gives us the total heat transfer rate. So if we substitute everything in here, so we will get this expression. So we already derived this expression, the relationship between the mean velocity and the radial velocity. So if we have a constant heat flux, if Q heat flux is constant, that means the second derivative, so second derivative of temperature will be 0, right? So that means so this expression is going to be simplified further. It's going to be simplified into this form, which is T mean times AX plus B, and this is a constant now. This is a constant here. So that means you can integrate this, and after you integrate, you get this relationship. And if you use the boundary conditions at r equal to 0, T is finite. So this means the log term should be C1 should be 0. At r equal to 0, the surface temperature is equal to the pipe temperature. Then from there you can find the C2, and if you combine everything, you get this expression. So this is the temperature profile as a function of R and X. So, and if you want to calculate the mean temperature, we use the definition of the mean temperature. So that means, so divided by the integrated temperature across the cross-sectional area divided by the cross-sectional area, and then we'll get this expression. And if you rearrange this, so Tm minus Tx is equal to minus 11 over 48 times Q constant times D over K. And if you want to compare this expression with heat flux equation, H times delta T, so you can see H is equal to 48 over 11 times K over D. Okay, so this is constant. So if you have a constant heat flux, K times H over, H times D over K, which is the Nusselt number, is equal to 4.36. This is always a constant. It's telling us if you have a fully laminar flow and if you have a constant heat flux, the Nusselt number is constant. So that means this number is constant. And if you do the same derivation for constant surface temperature, you get a constant, another constant, which is 3.66. These are the most important finding of this analysis. So it is telling us if you have a laminar flow, fully developed laminar flow, so the Nusselt number will be equal to 3.66 or 4.36. If you have a constant surface temperature, 366. If you have a constant heat flux, 4.36. So since the diameter of the pipe is the same, so that means the local is the same as the average. So that means because the diameter is the same, it doesn't matter where you evaluate it, it's always the same. So if you average the constant, it's going to be still the constant. So this is also important to realize.